Hello, everyone. Welcome to the fourth session of the Natural Language Engineering Workshop. In this session, we're going to talk about the first surge at deep learning. But before that, let's talk about the significance of machine learning. In one of the past exercises, you were asked to detect the language of a text based on frequency characteristics of the characters used in it. That is an example of a deterministic approach, also known as a rule-based approach. Such an approach is fast and effective and should always be tried as a first go-to. There are occasions, however, where this approach becomes inefficient, especially in a high variance problem space. Take the simple task of opening a door using a doorknob as an example. Let us imagine we're designing a robotic arm capable of doing this task. There are various types of doorknobs. They can vary in shape, size, and height based on installation. It is not trivial to account for all of these variations with a set of rules. Even if we can come up with a complex system of rules, every time a new doorknob comes out, we'll have to go back and make sure the system can still operate successfully. And if not, carefully add rules to the already complex system without breaking it, which frankly is not a pleasant task. The premise of machine learning instead is to infer these variations as opposed to hand design them. This automatically guarantees adaptability without expert intervention, which is much more cost effective, especially if the task at hand is a very specialized one. Okay, now that we've covered the significance of machine learning, let's get back to the eras of NLP picture. Basically, aside from the rule-based era, everything else is using machine learning principles to some degree. Historically, statistical natural language processing occurred before the deep learning eras. But let's start talking about the first surge of deep learning. We'll discuss statistical natural language processing in a separate video. All right, now let's talk about deep learning. Deep learning is a subfield of machine learning where learning and computation occur through layers of processing. What you're seeing right now is a multi-layer perceptron architecture. In this architecture, the data is input via the input layer. Some processing takes place with the weights, and the transformed data will end up at the first hidden layer. Again, processing occurs via weights, and the data will end up, well, further transformed data will end up at the second hidden layer, so on and so forth until the output layer. In this specific network, for example, you can see the input is 5-dimensional, R5. The hidden layer is 6-dimensional. The second hidden layer is 5-dimensional. And the final layer consists of only 2 dimensions. Each of these final dimensions can refer to a certain category, for example. If we're classifying between cats and dogs, one can refer to a score of the object to be a cat, and the other can refer to the score of the object to be a dog. The way a deep learning algorithm learns for supervised tasks is that it processes the input and makes predictions for the output. These predictions are compared to gold standard, the real output for the specific input. And the difference between the two is calculated using a cost function. The cost function will determine the error. The error is backpropagated through the network to fix the weights and update the weights to better predict the present category. If the error is big, you can expect more aggressive adaptations in the network. Otherwise, the changes will be smaller. All of this is possible by an algorithm called backpropagation. You have access to a tutorial on backpropagation in the course material directory. Make sure to take a look. Now, why is this depth of processing important? Basically, why does it matter to have more than one layer, one hidden layer, to process the input data? Or does it matter at all? The depth of processing significantly matters in natural language. Let's take a look at this example. Let's say we're in a speech recognition and natural language understanding domain. Basically, what we'd like to do is understand and input acoustic signal and interpret the meaning of the signal. Now, let's imagine we have three signals: mat, rat, and dog. From the acoustics perspective, you can see that rat and mat are very close to each other. Basically, you only have one consonant that is the difference between the two. Other than that, they're almost identical, acoustically speaking. So rat is closer to mat acoustically than to dog. Now, to be painstakingly accurate, we cannot interpret necessarily the written language for the sound. But that difference is trivial for the present case. All we need to know for now is that rat and mat are acoustically similar, and there's a sharp difference between rat and dog. Now, if you go to the semantic space out of the acoustic space, you'll see it the other way around. Basically, rat and dog, although not sounding similar, are actually much more similar in meaning than what rat is to a mat. Both are animate, both are animals, and mat is just an object and is inanimate. Now, if we are of the belief that these objects, mat, rat, and dog, acoustically and semantically refer to the same object out there in the world, then we can infer that the transition between these two spaces, basically going from the acoustic signals to mental representation of these objects, is nonlinear. In other words, if we think of the signals actually as input dimensions of a neural network, and these as some transformed vector representation of the same object, going from the acoustic space to the semantic space, to be loyal to the reality, is nonlinear. More specifically, mathematically speaking, there is no way that we can have a linear equation that can transform these vectors to these vectors. That is because the relative distance of these objects is changing throughout this transformation. And linear transformations are not capable of doing that. Now, you can tell me, well, this is an argument for the need for nonlinearity in machine learning. And maybe it's not an argument for the depth of processing in machine learning. And that's true for now, because we only have one nonlinear transformation so far. But if you go to the next layer after the semantics, such as putting objects together to mean different things, such as sentences, or even the next layer, pragmatics, where you can be sarcastic, for example. So your sentence is saying something, but you actually mean something else. All of these are more layers of nonlinear transformations and can only be achieved by depth of processing. Okay, now let's get back to our multi-layer perceptron architecture and see what's actually happening through the layers. You start with a linear equation that basically multiplies the weights with our input and adds some bias. And at each layer, you use one of these common nonlinearities. One is a sigmoid function. One is a hyperbolic tangent. There is rectified linear unit, ReLU. Also, there is leaky ReLU. ReLU is a special nonlinearity where anything at or smaller than 0 is 0, and above that is linear. Hyperbolic tangent is similar to sigmoid function, with the difference that it goes from -1 to 1 as opposed to 0 to 1. Now, let's take a look at the first ever deep language model. A language model predicts the next word in a sequence. That's all it does. Yasha Bengio and his colleagues in 2003 designed this neural network that can do the same thing as non-deep counterparts at the time did, mostly by hidden Markov models and later by conditional random fields. This algorithm wasn't adopted immediately, and the reason for that was the competitors had much better computational efficiency. Now, you can see there are indices for words, and then the word representations are looked up from a table. We can think about this as a projection layer. And then these representations are basically the first layer of the network. And the rest of the processing will happen very similar to multilayer perceptron, with the exceptions that there are optional skip connections from the representation, from the word representation, so the projection here, all the way to the output layer, right before the softmax. The other difference is that the input and output are timed. So basically, you have WT minus n plus 1. Let's think about it, WT as WT minus 3, WT minus 2, and then WT minus 1. And then you're predicting WT, or you're predicting the word at time t. With each additional word representation, there are lots of connections to be added between these two layers. So basically, you have the history, a few words in the past, depending what your n is, how far you're looking back, and then you're predicting the present word via the softmax layer, the word at time t. Now, let's take a look at the equation. Basically, your entire neural network is the function g that for each word I in the vocabulary and a set of words in the history, WT minus 1 all the way to WT all the way to WT minus n plus 1, and their corresponding projections, it can predict the probability of the ith word in the vocabulary. It's basically saying among all the words known to me as a language model, would like to know the probability of each one of them when predicting the next word. The probabilities are computed by a softmax function, where probability of WT, selected target word from the vocabulary, is conditioned upon the history of words as stated by the network. The output neurons each will have an output Y. For this specific selected WT, there is an output Y. And the value A to Y WT is normalized by the sum of all possible Ys. So basically all the output neurons. Each one represents, again, a word in the vocabulary. Therefore, we can have a probability estimation. Basically, we're searching for the optimal parameter set theta that maximizes the training corpus penalized lag likelihood. Again, we're maximizing the probability of the training corpus here. We have a weight decay penalty term here. So for each WT in the corpus sequence, we're predicting log likelihood. We're computing a log likelihood. We're summing the log likelihoods for the words in the corpus and dividing it by the number of words. Obviously, the higher that number is, the better we predicted the probability of the corpus, which is 1. Benjio 2003 calls that C layer the feature vector layer, board feature vector. It's basically a lookup table. Nowadays, we usually call them projection layer. We project from an index into an embedding space. That word representation layer is your embedding space. Again, make sure you go through the backpropagation document in your student materials directory. So by adding each word to the time steps, if you have a bigger sequence, you will have a lot of multiplications or linear algebra operations of some sort to cover because it's a fully connected neural network. The vanilla RNN architecture is a remedy to that. So basically, in an RNN architecture, the weights are shared across time steps. You don't need a new set of weights for each additional word that's added to the sequence. In a recurrent neural net architecture, as you can see right here, the entire network is just a recurrent layer. So basically, inputs come in at X, outputs go out at Y, and there is a shared set of weights for the input, shared set of weights for the recurrent layer, and shared set of weights for the output layer. If you unfold it, you can see that these weights are shared and get repeated. The U matrix, which is the transition matrix from HT minus 1 to HT, is not really shown here, but it exists. Let's just call it F. Because of such an architecture, now we're able to train longer and longer. We'll actually train on longer and longer sequences. And in a very much more computationally efficient manner. So basically, we don't have an infeasible number of weights to train when the sequence gets larger. So let's take a look at what happens. Basically, your xt minus 1 gets input to the network. There's a input weight multiplication. You get your hidden state. And then if there is an output to be created, you have your output weights, being applied to your hidden representation, and then creating an output. Which, if it's a neural language model, for example, it's going to be a word that's generated. Let's take a look at time t, where you get an input. So in addition to the input x at time t and the input weights, you get your hidden state receives input from the previous hidden state. Well, a transition matrix, weight matrix is applied here, but you keep that information to some extent, and then you create the output. So basically, your output y is indirectly dependent on your input xt minus 1, where the information preserved in the hidden state. All right, and that's very powerful. So even the final output is to some extent dependent on the first input. That's very powerful, although computationally very efficient. Okay, Now, there um, there are various neural nets, recurrent neural net architectures. Uh, as far as vanilla, and you see why we call it vanilla in the future, but as far as vanilla recurrent neural nets are concerned, there are two that are very common. One is the element network and one is the Jordan network. Now, can you pause the video and actually realize which one of these, element network or Jordan network, is represented by this graph? Okay, I assume you've paused the video and by now you know the answer. So let's go through the equations. In the element network, you have your HT to be the result of nonlinearity and activation function applied to the summation of the terms here, which are the input weight matrix being applied to the input vector, the plus the transition matrix being applied to the previous time steps hidden representation or the hidden state, and then a bias. So basically, nothing here contradicts what you see in the image. To construct the hidden representation at time t, you receive input from the input at time t and from the previous hidden representation or hidden state. In output, you just use the output weights and an output bias, and there's a nonlinearity. All right. So this goes well with the graph here. How about the Jordan network? The Jordan network, you can see that almost everything is the same. You have the same weights are applied to the input. You have the bias similarly. Aside from the fact that instead of getting a input from the previous hidden state, you get an input from the previous output. Right? The output vector is multiplied by the transition vector and then added to the rest of the terms to create the present hidden representation. So you have a connection between yt minus 1 to ht. All right, so far you know recurrent neural net architectures, you know the feed-forward architectures applied to natural language, and you know how they fare against each other. Basically, you know that recurrent neural nets are much more efficient, faster, and enable a deeper computation. Given that given that they're more efficient, we afford to have longer and longer sequences. That, however, presents its own set of problems, namely vanishing and exploding gradients. In vanishing gradients, your gradients go all the way to zero. And just as a reminder that your gradients are the partial derivatives from your signal, from your error out of the cost function, propagated back to each time steps to update the weights. These partial derivatives will help you update the weights to direct the input to generate the correct output closer to the ground truth. All right, so that's with the reminder, but basically, if your gradients are zero, your weights won't change, and you won't be able to decrease the error that's generated. Well, and that's the result of the incorrect output that you've generated. And your network just stops training. Although you're training it, it just stops improving. So that's how I see your kind of the vanishing gradients effect for iterations, speed batches, instances, or while you're training epochs. You see that your network doesn't really improve anymore. How you detect exploding gradients, however, is that you notice that your network generates nans in Python, non-number. And that means that your gradients have become so big that have moved so far away from the regime of sensible gradients that your network is just shooting off by large. And it's so far away that it's very hard for it to figure out a way back to the actual regime that's relevant to the problem at hand. So that's how you detect vanishing and exploiting gradients when you're training neural networks. Again, why that's the problem for recurrent neural networks? Because they can be very deep. Um, Deep recurrent neural networks are trained using an algorithm called backpropagation through time. You have the mathematical details of the algorithm in your student materials folder. So please take a look. It's important to know the details, but basically it enables us to backpropagate the error all the way through these uh, recurrent hidden states. So in this video, we talked about the importance of depth in natural language processing, and we covered feed-forward networks applied to NLP as well as recurrent networks applied to NLP. Now you appreciate the difference and you're familiar with the vanishing and exploring gradient problem. There is another point that we kind of touched upon when we talked about the significance of depth in natural language processing, and it's a significance of nonlinearity. To know more about that concept, take a look at the significance of nonlinearity video, which walks you through experimentally a classification problem where you can see how algebraically and experimentally nonlinearity is significant in processing, you know, over their mathematical concepts, but it applies directly to natural language processing as we have covered here. All right, that brings the present video to an end. Thank you for watching, and I'll see you in the next video.